Okay.
Alrighty, guys, we're live. So, everybody, thank you for coming today to the ValleyDAO Science Spotlight. I'm Thomas Alexander. I'll be your host today. I'm a contributor here at ValleyDAO, but it's not about me. It's about our special guest, Dr. Rebecca Vaught from Heron Labs. She's got a really cool presentation for us today, some insider information that getting the scoop on. Yes, thank you to everybody who's attending in person or watching this recording later. People who are here, make sure that you are active in the chat. We're going to be keeping up with that, and those questions will be asked later. So without further ado, Dr. Rebecca Vaught, want to take it away?
Sure, sounds great. Hey guys. So yeah, I'm gonna go ahead and just share my screen. Oh, host disabled participant screen sharing.
Let me just fix that 1 second. Okay, try it now.
Let's give it a go. Yeah, perfect. All right. Just minimize this. And just go present. Cool. Can somebody give me a verbal on whether or not you can see my black slides?
Can see it just great.
Okay, I'm just gonna do perfect. Awesome. Okay, good. Yeah, so thank you guys so much for being here. Thanks so much to the ValleyDAO team for one, putting together the science spotlights, and then two, inviting me. This is a lot of fun. It's been a while since I've done kind of a talk like this, but I really enjoy kind of speaking to folks that are interested in our science, and hopefully we can have a great discussion today. So just a bit about the agenda, or I guess some housekeeping items. So I am sitting in an airport right now. I'm hotspotting off of my phone. This was not the way I thought this day was going to go. I thought I was going to be a bit more stable, but we're rolling with it. So if my connection goes down, guys, just hang tight. I will try to get everything up and rolling again. So just talk amongst yourselves. I'll try to get it back up and running in the background. So I'm going to tell you guys a little bit about me and my background, kind of our perspectives, or the perspectives of Van Heron Labs on the industry, tell you a little bit about the company, and then we'll go into some Q&A and discussion. And really just want to kind of keep this, fluid and loose, and just see where the conversation leads us. For those of you guys that don't know me, this is a little snapshot of the pies that I have my fingers in. So I'm the CEO of Van Heron Labs. I'm also an advisor for ValleyDAO, have been kind of immersed in the community, the collective for since the beginning. It's been awesome to see all the progress that's been made. Some of the cool research that's getting funded, the scientists and companies that are being supported. It's just a great community. I know that some of you guys on the call have maybe just joined because you're familiar with me and with Van Heron Labs, but I'd encourage you to get plugged in and see what's going on. There's a lot of great things happening, and a lot of ways to add value. I'm also a Longevity Biotech Fellow for 2023. Relevant to this call, I also sit on the board of the Cultured Meat Modeling Consortium, and I'm on the board of BioAlabama. I also advise a few other companies that aren't listed here. And so you can probably tell from some of those logos, I've got a very varied background, which I will try to now encapsulate. And this sort of varied background plays a big role on why I started the company and some of the technologies that we're focused on. So I did my bachelor's degree was in molecular cell and microbial biology. While I was doing that bachelor's, I was doing 3.5 years of undergraduate research in marine biology, physiology, evolutionary genetics. I then went on to Monash University and did a Ph.D. in evolutionary genetics, where I was very focused on fitness, aging, metabolism. Had a very diverse Ph.D. thesis, had some very interesting chapters. And then for the past 3.5 years, I've been running Van Heron Labs, kind of taking these systems approaches towards sort of problem solving in the biotech and the synbio biomanufacturing space. And so I've also been kind of getting acquainted with a lot of new industries. One of them, at least a few years ago, we were completely new to cell and tissue culture, sort of the mammalian side of things. And so now the company is very much dually both in the microbial and then also the mammalian or the cell line space. So I'll try to speak to that a little bit today. And so, yeah, I think a lot of folks on the call, certainly one of the things that we're very motivated by at Van Heron Labs is that this premise that the future is going to be built with biology. I probably don't have to explain that to a lot of the folks that are here, but for anybody that's unfamiliar, the rate of these new biological innovations that are now coming to light have actually outpaced Moore's law. So we are hitting kind of this critical inflection point where new biological technologies are being used to improve or even replace more traditional technologies, more traditional industries, and this is only going to accelerate. So a lot of these changes are being driven by advances in computing, AI, genomics, new biological capabilities. And so this bioeconomy, or this word that sort of encapsulates all of this across all of these industries that you sort of see depicted here, are really addressing a lot of global challenges. Obviously, COVID-19 is a good example of that, but other industries are also going to be starting to transition into these better, faster, and greener biological innovations or improvements. And so folks like Schmidt Futures have actually predicted that these types of biological transitions are going to underpin the entire global economy in the next few decades. So it's incredibly important. But the problem with this is that this bioeconomy really needs better supporting infrastructure. So I was sort of young during the computing revolution that happened in the 80s and 90s and early 2000s. But one parallel that you can draw is that with each advance in silicon chips, what we were able to do was gain advancements in computing and then move humans in society forward. And I think the same sort of technological path is going to happen with some of these biological technologies that I was teasing on the previous slide. But the problem with this is that bioindustry, biotech really needs better chips and then also ways of producing those chips. And so this was a huge driver for us starting the company, and this is what motivates us now. And so what are some of the areas that are sort of outdated or need better tools, picks and shovels? And so these are the three that we are very interested in, and some of the places where we see sort of not necessarily failures, but people have been doing things the same way for decades, and these really need to be updated. So the way that cells are engineered, fueled, and cultured. And so why does this matter? It matters for overall success. You guys probably know from the synthetic biology space that some of the technologies that people are working with are incredibly risky from a commercial standpoint. So the chances of failure are fairly high. So if you have better ways to engineer your cells, better ways to culture them, and then scale up that new biological technology, your chances of success and ultimately making a difference for the planet, for human health, are much greater. We have to reach, as you guys know, to displace something like the traditional chemical industry or traditional agriculture, you need incredible scale. And so that's where some of those points are going to come into play. Cost, these are commodity industries. We have to be able to make very aggressive cost targets, keeping in mind scale and success. We need better quality for some of the folks that are kind of on the human or the mammalian side. Cells are being used as therapies now. And the way that we fuel those cells and harness those cells is going to be incredibly important once you inject them into a human being. So the way we're treating these is very, very important. And then it matters for time. So one of the key factors that matters for industry is how fast we can turn this around. Again, for a COVID-19 example, how fast can we go from a 96 well plate to shots and arms? And so Van Heron Labs is really kind of addressing all of these key areas that we see. The first technology, or one of the technologies that we're really passionate about, is media development. So this is actually the fuel or the broth that the cells are being propagated on. And so our tagline is, and we still really like this, that we're rocket fuel for the new bioeconomy. And so again, just to give another computing example, the 2000s were sort of defined by programming computers. Around 2010, synthetic biology was really starting to hit its stride. Ginkgo Bioworks came on the scene. And now what we think is going to be really, really important is this sort of third phase, which is programming the biological environments that these cells are harnessed within. And I'm going to come back to this slide at the end of the presentation and try to convince you that these biological environments and new ways of programming them is very, very important. And so I teased kind of our first technology that Van Heron Labs focused on. This is a new platform that you can utilize to create better nutrient compositions for cells to grow or produce biological materials with, or become a therapy themselves. So I don't know how familiar you guys are with culture media. Pretty much ubiquitously across microbial cell culture and also mammalian cell culture, there's a lot of traditional formulations that have been utilized since the 1950s and 60s. They really have not advanced. Some of you guys will be familiar with the fact that to kind of cover up the deficits in these formulations, things like animal products and other extracts are usually utilized to sort of make up the difference, give the cells key growth factors, and sort of propagate the systems. But we have a very interesting technology, or an interesting underlying platform, in that from genetic data, we're able to see an optimal suite, or we can optimally predict both the macro and micronutrients that a particular cell type at a particular context is going to need. And then we use chemistry and biochemistry to turn that into a media formulation. So this is sort of a precision nutrition technology. And just to bring it back to the rocket fuel example, this is sort of custom rocket fuel for your cell or your biosystem of interest. And so this works across, any cell type that or tissue or organism that has genetic data. We can do this. So even kind of more obscure things like agriculture. And this is kind of for the media nerds out there. There are other metabolic approaches to predicting what nutrient utilization is going to look like across cell types. Some of those, I'm just going to briefly go over these, are flux balance analysis and GEMS. Compared to our approach, we see significantly better outcomes across recombinant protein production and cell proliferation. But you can read about this. We've got a light paper if you really want to go deep on the media development and the platform and what this looks like for industry. You can find a link to that on our website. And I'd also be glad to answer any questions at the end of the presentation. But what I want to talk about for the rest of the time we have together, unless there is Q&A about, I could talk about media all day. We are now kind of a technology company. So from making that first platform, we've now developed a lot of other technologies to, number one, complement our core media formulation services. Also kind of solve big problems that we see across the industry. So if we identify a technology that is better, faster, and cheaper, we're very quickly trying to figure out how to turn that into an R&D program, and then trying to figure out how to actually make that a commercial product and get it out there into the marketplace. And so this has been these new technologies have really been our focus over the past year or so, and now we're finally getting to a point where some of this new stuff is coming to light, and I'll talk a little bit more about this. We've got some pretty cool things happening. So just to bring it back to our core verticals, I teased this when I was going over the core platform slide, but we work across a lot of different industries. It's a really fun day at work. I went from talking about fish cells in culture, and then mammalian cells in culture, to microbes in culture, all across, things like biofuels and cell therapies and monoclonal antibody production. It is just like we do everything. We're definitely not a focused company, but it's a lot of fun, and I wouldn't have it any other way. So we're working across a lot of different industries simultaneously for a lot of our technologies that we're now focused on. And this is sort of a snapshot. This is an ugly slide. Sorry, this is just like a lot of text, but these are some of our R&D programs that we have right now. A few services for custom media development. We have a service called Cerex that helps folks for both mammalian and microbes transition to chemically defined culture to get rid of some of those extracts and other things that folks are using within their media formulations. We've got a new, very cool transfection reagent, the Universal Microbial Agitation Culture Additive. Terrible name. If anybody has any suggestions on that, would really appreciate it. And I'm going to show you guys some data that we have around that. We've also got a lipid nanoparticle for therapeutic delivery. We have an intern right now that's working on a supercharged microbial production strain that's got a new type of metabolic system embedded within it to increase recombinant production or heterologous production. And then we were going to actually, up until this point, we've been kind of a services company, and we're going to actually make a few physical products and sell them via e-commerce. Some of those are an antibody expression supplement, an E. coli expression supplement. We're also working on some human nutritional interventions from the platform, and then a solid media supplement for cloning. And then what we really want is to be able to turn our core platform into something like a SaaS or a user interface where people can upload their sequences and get their nutrients back. So there's a lot going on at the company. It's keeping me on my toes right now. But yeah, it's good fun. So if anybody has any questions on this, I'd be glad to talk about it more. Okay, and so I know folks are here for this. So our microbial agitation additive, we have seen some fairly crazy results, or maybe seeing some crazy results for doubling time in E. coli. So for folks that are unfamiliar, E. coli is predicted to double somewhere between 20 and 30 minutes. And based on the results that I'm going to show you guys today, it could be that they're actually doubling on the rate of, five-ish minutes, have even seen down to something just a little bit over 4 minutes. So we discovered about a year ago, a little over a year ago, this sort of novel molecule that had some very interesting fluid dynamics properties. Started doing a lot of research, realized that it could maybe be utilized as something like a bioreactor additive to improve the fluid dynamics of liquid culture systems. And so we have finally finished kind of our behind the scenes R&D sprint and have kind of put some of this stuff into practice, looking at a particular E. coli strain that we have. It's a BL21. I guess just a little bit on how we have our culture set up before I start going into some of the data. This has all been in 40 mil culture flasks. We're using stir bars, and then we're using magnetic stirring. So it's kind of you could say a mini bioreactor setup. So we're not shaking, not stirred, not shaken. Is that right? Yeah. So so the molecule is predicted to improve the gas dynamics within these cultures, which then would improve the mass transfer, which may lead to greater biomass accumulation. There's also some evidence in the literature that it could be actually directly improving some of the cell wall dynamics to improve shear stress resistance. So this is our craziest experiment that we've seen so far. So this is the data. Sorry, it's not the most beautiful that you guys saw the LinkedIn post about. So for this particular experiment, what we saw across the treatments was that over a 22-minute period, the treatments doubled about 5 times, but the controls only doubled once. So you can see kind of where the controls start and then where the treatments are. So for our culture setup, they really start to peak out around OD 1.2. They will grow all the way up to OD 2.5, but they've really kind of hit the top of their growth curve around OD 1.4, 1.6, and then everything starts to kind of peter off. So these guys really like their entire growth curve within that 22-minute period. Also, I should mention that these were done with 16-hour overnights where there was no additive, so just straight LB media. We have replicated this experiment about 9 times. I'm going to show another one with kind of the more typical results that we see. This one was a little bit of exaggerate. Well, I don't know. You'll see on the next slide that 30 minutes seems to be plenty of time for these guys to finish their entire growth curve, which I realize is crazy, and we're going to talk about this. So some of the things that are interesting is that we see that this effect is context dependent on the nutrient environment, which I love. So we've done this experiment with a half X LB, so a diluted LB and it's about a twofold decrease in the overall growth rate or cell density over time. We've also done an abiotic test of the same conditions with no cells added to make sure that there's not some sort of weird precipitation from there being greater oxygen in the system and causing some sort of like trace metal or something to precipitate out of the media and affect the OD, and that be this sort of result that we're seeing. Let's see. Yeah, so this is kind of our more typical result that we see. So this was over the course of about 50 minutes. So the cool thing about this is that you can see, I said that our system sort of peaks out at OD 1.4-ish. You can see the 5 millimolar treatments. They've already maxed out in that 50-minute span, so we couldn't even capture them in enough time. The 3 millimolar is hitting their peak, and then the 1 millimolar is getting there. So it seems to be some sort of it seems to be biological, at least based on the ODs and the patterns that we're seeing. And then I'm going to go over some more specific data. I don't know how bored you guys are going to get with all this. This is our pellet wet mass that we see. These are actually not the correct error bars. We had more error for this 3 millimolar treatment. Google Sheets is just stupid. But we see kind of the same thing. So these are the CFUs. Obviously, there's a discrepancy here between the CFUs and the results that we see for OD. Still trying to kind of work that out. Our pellet dry mass is consistent with the results that we see for the OD reading. So this is about a 27% increase over the controls. The OD readings that we're taking are about a 25x increase over the controls as far as cell density is concerned. Okay, so we are sending out samples to people. If you don't believe us, you can try it yourself. If you are interested in trying this out, you can hit me or hit us at contact@vanheronlabs.com. My email is rvaught@vanheronlabs.com. We'd be happy to send this to you. We've got some capabilities at our lab, but we don't have, the best bioreactor setups. I don't have Sartorius systems or anything fancy that I can throw this stuff in. If you've got a great system for kind of quantifying things and want to help us out and help us characterize this, we'd love to talk to you. For the next 2 weeks, our experimental slate, I hope people's eyes aren't glazing over with all these details. We're going to redo those CFU counts and see if we can figure out what's going on. I'm going to redo the wet weight again, and then we're going to start actually doing some protein induction to look at recombinant production and see what we can get. And actually I should say, that's what we were trying to get to. So we designed this to be an expression aid for microbes. And I actually set up the first experiment just so the team could see how you run a growth curve. And we saw these crazy results. And now we've gotten totally derailed for like the past 4 weeks or 5 weeks even now. But it's been good fun. It's been good fun to do this. So happy to hear people's thoughts, and yeah, please reach out if you're interested in trying this. Okay, and so this is one of the things that I want to end on. So in the beginning of the talk, I said kind of 2000s programming computers, 2010 we're programming biology. 2020 Van Heron Labs emerges on the scenes, and we realize that programming these biological environments is very important because what we've maybe unearthed here is this new capability with E. coli that let's just say I'm right. Just suspend disbelief for a minute, and let's say I'm right. Let's say that E. coli can double in 5 minutes rather than 20 or 30 minutes. We've just discovered something about biology that we didn't know before, and it didn't come from tweaking the cells. It came from tweaking the environment. So the environment that the environments that we're using going forward are incredibly important. I hope there's other companies that emerge that sort of take our thinking on this, is that, this is maybe where the secret sauce is. We have incredible control over, genomic information. Synthetic biology is practically automated. There's probably people shaking their heads on the call. They're like, I'm metabolic engineering right now. This is not automated at all. But yeah, so there are companies that have automated this greater than the automation that was around in 2010. And so now where we really see our future is on this this back end of things, actually trying to program things going into the bioreactor so that we see some incredible results and we're able to move the industry forward. And then, yeah, so the last thing that I want to end on, So I don't want the discussion period to be just about me or Van Heron Labs or even some of the data that we've seen. Certainly we can talk about it, but I'm very open to just discussing the industry more broadly and what you guys think and the way things are moving. And I realize there's been a lot of kind of sadness over the past few weeks. There's been layoffs. The outlook for biotech in general is very gloomy from an investment perspective. The banks are failing. Like, what is going on here? But sort of, I think the weight of the world is actually going to be a way to catalyze some of these transitions in the support for synthetic biology and biomanufacturing more broadly. So the fact that we're all scrambling to find raw materials, the fact that we're scrambling to find these animal products that don't exist, the fact that energy is really high, this is going to cause people and governments to really take note of some of the things that are happening within the biomanufacturing space, and I think get things to move more rapidly. So I think all the clouds that are hanging over are actually maybe a ray of sunshine for making people realize that synthetic biology and some of the things that we want to make in the future, this sort of world that we envision is not this this far off thing, but the way that things have to happen when we can't get raw materials and there are no animals, and the energy costs are incredibly high. So overall, I would say my outlook is still positive, and I hope yours is too. Okay, and so now I'm going to open it up to some Q&A and discussion. Happy to talk about anything that you guys saw, what it's like to be a biotech founder and sit in an airport and give a seminar, or how do you bootstrap a company in Alabama, just anything that you guys want to talk about. I'm open to it. So with that, I'm gonna wrap it up, and I will stop sharing my screen. And yeah, happy to have a chat. Thank you guys so much for listening, and thanks again to the ValleyDAO folks for having me here.
Oh my God, that was so cool. That was such a great presentation. I definitely could have some things to say, but if anybody in the audience has any questions, now's the time to unmute, jump in, or drop them in the chat. Camilla?
Yes, hi. Thanks, Rebecca. This was really interesting. I actually agree with you in terms of if you tweak the environmental conditions, you can get so much more out of your microorganisms. It's just that you have so many variables of it. But as an example, during my PhD in one of the side projects that we're doing, I was expressing proteins in E. coli, and we accidentally found this method. It's completely just environmental conditions that improves the protein expression by 4 times. And we haven't done any engineerings, no genetic modifications. It's literally just the media and the conditions. So I think it's really interesting, and I'll be very curious to see your results. Sorry, so this is not questions, just more like a comment. So I think I'll be really interested to see your results, especially if you do the same growth curves, but with a plasmid in it or any genetically modification, just to see if you still have that same fast growth phenotype. And then obviously if the fast growth is beneficial for the protein expression of interest.
Yep, sounds great. I should also say, so these are, they are carrying a plasmid, so they're under selection. So they've got a recombinant enzyme, these strains that we're using, because like I said, that's what we were trying to get to. But yeah, it'll also be interesting to look at other E. coli strains and see, well, it'll be interesting to look at various cell types. So the folks that are testing this now, we've got one person, we've got yeast, we've got E. coli, we've got algae, I'm trying to think if we've got any other bacterial strains, but I think it's only E. coli. So we've got E. coli, Saccharomyces, and algae. So we're hoping to get some other interesting cell data in there as well.
Do you have any preliminary data from the other species? How that affects them?
Not yet. So we just started sending samples out the door about 3 weeks ago. And so, it took about a week for shipping, and now we're waiting on folks to kind of report back.
So if I can ask a question, and zooming all the way back, pre Van Heron Labs, even pre-PhD, I think a lot of us in this space have had those formative moments or that epiphany that drove us to want to be involved in this bio revolution. So what was the catalytic moment for you as a young woman that perhaps drove you to go into biology or science in general?
Oh yeah, good question. I've always loved science. My dad was an evolutionary biologist living in Alabama. And so that had a big impact on me at a young age. Because I'm from a really rural, I'm from a town of 1,500 people. I just don't have a Southern accent, but I went to Title I schools my entire life, which means that over 70% of the kids live in abject poverty. So it doesn't get any more rural than the place that I came from. And so the sentiment around science was always very controversial, and things started to get strange when I got into high school and we started discussing topics like evolution. And so it was really important that my dad was a biologist and showed me how important it could be. And then he worked within industry, so he was doing like enzymatic catalysis for large industrial fermenters. So I maybe the seed was planted super early, and now I've worked on, that hasn't always been the field that I've been in, but that is interesting. Maybe I've circled back now to kind of where my roots were in some of the conversations that I overheard as a kid, and maybe wanting to add value into a similar space. But I've always just found science to be really fascinating. And then it was just, you end up being good at or caring about the things that you're interested in. So it was always, I was really unprepared for college from being from that rural place. And so I went to college, the highest math I had ever had was algebra 2. And now I think kids are taking algebra 2 in, like, I don't know, elementary school. It's just ridiculous. So I went off to college. I struggled really, really pronounced. I struggled a lot and had to study, and biology was the one place where I was just excelling and making like perfect grades. And then that was really reinforcing, like, everything. It was like the world's crashing around me, but I still have this little science pillar like propping me up. And then that was motivating to get through the rest of my classes. And then I graduated with great grades. But yeah, it certainly has been, I don't know if it's been a linear path, but yeah, I've always just loved it and enjoyed it. And it's the thing that I can't stop thinking about and doing, for better or worse, right? Like, there's nothing like better or worse than science. Just like the highest highs and the lowest lows, I think. But yeah, I wouldn't have it any other way at this point.
Awesome. Maybe I can hijack one more time, but I do want to say, if anyone else has any questions, please raise your hands and I'll shut up. But so you speak about the highs and the lows. Could you give us some examples of some of those moments throughout your career?
Yeah, I mean, my low point was grad school. So I was in it, just to be clear, I had an incredible project. I had incredible supervisors, but I was doing, I think I mentioned this, that I was studying aging for my Ph.D. And I was working in a fruit fly system, and the aging, like the longevity experiments, are brutal. You're tipping the flies every day. You have no, like 2018, I did not have a single day off. I worked 8 hours a day for 365 days straight. And so just the mental like slog of getting through that. And then at the same time, knowing that my project was really, really important, was just, yeah, it was just so hard to get through. So that was a low, but I think what came out of that was that it really, like, I think if I hadn't been through something that tough in graduate school, I probably wouldn't have started the company. And so like having that, being like, and actually one of my committee members at the time, he was like, everything is going to be so easy for you now. Like them watching me go through that, they're like, any obstacle that comes up, you're going to be like, well, it's not as bad as those aging experiments that I did. The crossing scheme that I had only had a 1% chance of success. And in fact, the first time that I did it, it failed because the infrastructure at the school that I was at was just terrible. Not to throw Monash under the bus, but they need to improve their infrastructure. And in fact, it did fail. And during COVID, and they lost probably $7 million worth of specimens. But Yeah, so just like knowing, like looking at this genetic crossing scheme and be like, yeah, you have a 1% chance of success. It's like, it's crazy. And then you're like, oh, well, I'm just gonna, you know what? I think I've got, I think I'm gonna start a biotech company now. It's like, oh, this will be fine. So I think you take, yeah, the good with the bad, I suppose.
Yeah, yeah, no, that was a great answer. I think I definitely can relate to that personally. Like my experiences throughout doing research kind of gave me a chip on my shoulder and made me want to
Mm,
dive into the world of entrepreneurship.
yeah.
Where ironically you have higher than a 1% chance of success.
Yep.
Yeah. Just right, just.
Yeah.
Just a smidge. So if you let me jump in, I have a question related to your PhD. I noticed that you work in so many different fields of science under the umbrella of biology. As somebody who always has trouble locking down on like specific topics when asked, like, oh, what kind of biotech do you
Yeah.
do? Um, how was it transitioning from like doing that one single topic for your PhD to essentially starting a platform company?
Yeah, it was it was a lot of it was definitely a transition. A lot of we work with a lot of genetic data, which is what I did during my undergrad. So our current bioinformatician is somebody that I worked with during the whole time I was doing undergrad research. And so it was a little bit like getting the band back together, but then like a remix. It was like everything was like a remix. It was like we're gonna do for the genomics. We're gonna get Damien, who's our bioinformatician, and then it was like we're gonna fire up microbiology again, and because we started out doing microbial experiments uh, in the early days. So just I'll also back up and share a little bit of the story of VHL because I don't know if people know this, but I started the company in January 2020, so it was great timing. And we were in the Texas Medical Center in Houston, which has 22 hospitals. So it was incredibly scary in the early days of COVID. Like I think, so we were being accelerated by a group in Houston called Inventure, which is a nonprofit, and instead they shut down all of the programs. To give you guys an example, they're very much like Nucleate, and I think actually Nucleate and Inventure are now working together. They shut down all of their programs. They were like, we're going to divert to crisis response in Houston. And so people were just trying to figure out, how do we put 12 people on a ventilator? How do we get PPE into the medical center? And so that was like the environment that we were in. And we ended up, at that time, Van Heron Labs was just a concept. And we ended up like, we're building a lab now. We're going to try to make vaccines or help with vaccine production. And that's what we did. So the reason why we're called Van Heron Labs is there was a family called the Heron Family. I think I mentioned that my dad used to work in industrial catalysis. His best friend and coworker, James Heron, had collected a lot of laboratory equipment over the course of his career. And he unfortunately passed away. And when that happened, his family donated the equipment that Van Heron Labs got started on. So I drove to Alabama, drove the equipment back to Houston. I started doing media optimization for companies that we knew were working within microbial systems, and did that successfully from a home lab. And Sunanda's on the call. She was helping us during that time remotely. And so it was really crazy. And that's how the company got started. And then we forayed, and then because we were working on vaccine production, we started to transition more into mammalian work. And that's how we ended up back at HudsonAlpha at the Institute. And we have a strong collaboration with another company there that was working on a receptor binding domain vaccine, and they were doing that in a mammalian system. And so then I went from like furiously working in a home lab to like furiously learning mammalian cell culture for the first time, and trying to like produce a vaccine. But what ended up happening was the mRNA technology just beat us. But then at that point, Van Heron Labs was established, and so that's kind of how the company came to be. So to go back to like to be, I had to use all of my scientific background, I guess, to get to that point. So it did become like kind of a remix for all of the fields that I had worked in. It was like, you're going to have to use everything to be able to do this. So that was a long answer, but yeah, it was definitely very interesting. I mean, the other thing is that, there are underlying principles to biology. While it's very complicated, there are some things that are the same, and you can exploit those principles across different industries. I think it's a weapon now that I've worked within a mammalian system and can come back to microbial, because there's certain patterns and things that we pick up on that can be kind of a secret weapon when you're working in a new system, or can give you new perspective, or hey, let's try this. So again, I think it's all for the good.
Yeah, that's really exciting to think about how access to those tools really enabled you to bootstrap and had to think in ways that allow you to synthesize maybe broader topics than you might have in an institute, or if you had somewhere where you're working under more defined conditions towards more hierarchical defined goals. Not having that and being able to have that entrepreneurial vision to set your own direction and say that, well, there's to find those laterals from across biology lets you find new novel things like the media additive that you stumbled across, that who knows if that would have happened without access to that bootstrapping.
Yeah, it's a lot of fun. And yeah, we use a lot of like cross-disciplinary, approaches. We found the additive while we were doing mammalian stuff, and now we're using it for microbial. So yeah, I think it all just feeds within itself. I'm glad. The reason why we named it Van Heron Labs and not Van Heron something else is because I suspected, just based on knowing myself, that we were going to be doing a lot of different things and kind of bouncing around. And certainly in the early days, I think the folks that were here in the beginning, the reason why I'm sitting in an airport is because we're doing fundraising. So I'm going to meet with some of our investors, and certainly, there's a lot of investors who want you to stay focused. They want you working on one particular area. When they see that slide that you guys saw where we have 11 R&D programs, they're like, oh my God, it's like that's like a worst case scenario. And so we very much have had to find people that are aligned with us that look at that slide and all they see is just like the potential, and like, that this is a place where we can get in there and get your hands dirty. But you've got to find the people that are on your side and are aligned with that.
Yeah, we had a similar feedback as a DAO, which is crazy because you think about the whole principle being like network effects and that we have so many fingers in so many different pies. But yeah, we interestingly got the same feedback recently, and we're like, oh, okay. Compared to like Hair DAO, which are focusing on hair loss, which seems like a very focused and an easy thing to solve. But yeah, it's interesting to see that narrative coming out in those mindsets. I have one more question. Again, zooming, well, perhaps a question for you now, but maybe an answer you would have liked earlier in life. What's the one thing you wish you knew early on, as an early career scientist, but also as a founder in the space?
Ooh, I don't know. I don't regret the way that anything has happened. I certainly wouldn't change anything, because I think, like I said, there's a lot of like serendipity and things feeding on each other. And, like I mentioned, if I wouldn't have gone through hell in graduate school, who knows if I would even be here talking to you guys. So maybe, yeah, I don't know. Maybe ignorance is bliss. On that, I don't know if I would have wanted any more information. So yeah, sorry, that's not a great answer, but I think sometimes I think actually one of our biggest strengths has been that I'm willing to kind of go into areas that I'm blind in and being willing to learn. And so that kind of curiosity in the face of a lack of information, and just being confident that we can get the information or find the right people or find the right mentors that can support us, has been a strength.
I think you're the first person I've ever heard answer that question in that way, but it's definitely an acceptable and justified answer. Awesome.
Pretty funny.
I think it was great. Always be driven by curiosity, and never let the scale of the problems daunt you.
That's right. Because you may go in there and realize it's a lot more simple than, it's usually not in biology, but you never know. You should look into it first. It's like trust and verify, I suppose. Cool.
Would you
Go
mind
for
if
it,
we?
Hamza.
Oh yeah, Hamza, go ahead.
Okay, hello. Well, first of all, thanks for an amazing talk. A non-synbio person here, so you're attracting a very large crowd. I think that's a pretty good news. Right. So I have a wildly tangential kind of question, also maybe borderline moronic, but I think it's kind of fitting to ask such a question, to somebody like you, who's looking at these organisms and looking at how these things evolve. And I think you were mentioning extracting general principles from just by looking at these complex phenomena that may be surfacey in nature. So the simulation theory, can we design, and it's okay if you can't answer this in all its scientific glory, that's perfectly okay. So can we take you study organisms and their evolution, and can we look at the patterns that you're already looking at and design some tests to test out some aspects of simulation theory, whether we are living in a simulated universe or not? I realize this is overlapping with a lot of other disciplines as well, like information theory, for instance, or maybe even physics. But just like, what are your thoughts here? And again, it's perfectly okay if it's not an extremely well articulated answer.
Oh man, that's definitely that is a wild one. Also, I love, Hamza, you don't describe yourself as a synthetic biology person, yet you're like you're like this critical pillar for ValleyDAO. So you are a synthetic biology person.
Well, a lot of people at ValleyDAO would love to disagree with you, but go ahead.
No. You're in the family for sure. You've gotten yourself into this whether you like it or not. So, but yeah, to get back to the simulation theory, I mean, I'll give you my tangential answer. I think there are a lot of patterns out there in nature that, like physical, I'm talking about like biophysical patterns that are very similar, like, and I'm not even going to be able to articulate this very well because I've been up since 5 a.m. And am now low on caffeine. But there's physical properties, for instance, that govern how we age, and how things start to fall apart within a biological system. And so you have this, like, for lack of a better term, like these oscillation effects that you can sort of map. And in fact, there's a company that's actually studying this in Europe. I think they're moving to the US soon, and they've actually got a partnership with Pfizer. But people are kind of finding those sort of similar patterns across not just aging, but other biological phenomenon, other physical phenomenon. And so, it begs the question, is there kind of this underlying, pattern to the way that the way that things move? Does that if that is true, does that mean that there is some sort of simulation or some sort of overall governing thing? I'm not sure, but I find that really interesting as a concept, is that you do see these same patterns. For instance, the company that we have a partnership with, he's a hardcore theoretical physicist, and he loves to get mammalian cell culture data and apply equations that make sense for theoretical physics to mammalian phenomenon. And 9 times out of 10, he finds something. Ernie will be like, look, I just put this on top of my new experimental results. Look, it matches perfectly. And it's some, like, wave pattern from something that I'm not smart enough to even know what's going on. But yeah, so I find that really interesting. But as far as like setting up particular experiments to determine, simulation theory, gosh, yeah, that'd be a good question for somebody. Yeah, who's yeah. I don't have any great answers. I also, yeah, this is a bad answer, but like, I don't care. Like, I think there's a really good chance that we are in a simulation, just because like everything is just so cartoonish all the time. that I've almost like accepted it at this point. Like everything is just so yeah, it's just so yeah, cartoonish. It's hard to be believed. But I suppose like if you still have the same control over your circumstances, we're still all trudging through the same thing together. But I'm sure there's some great, biologists who, yeah, are probably working on this out there. It's definitely it's a great question. I'm probably not the best person to answer it though, unfortunately.
No, that's okay. No, I think that's pretty reasonable. So did this person that you mentioned, do you have their LinkedIn or something?
I don't know if he's on LinkedIn. The company is Foresight Biosciences, and he's their senior scientist. It's Ernie Curto. So he has a PhD. He's actually got two PhDs, one in theoretical physics and one molecular biology. And so he loves to put the two together.
Right. Okay. That's cool. Okay, sounds good.
That's a really interesting question, Hamza. Oh wait, getting an echo here. 1 second. There we go. Yeah, no, that's a really interesting question, Hamza. I actually thought about, I guess it's not simulation theory, but something I found really interesting was how, if you're traveling at high speed relative to the speed of light, you've got like relative effects on how you age. And there have been studies on people on the International Space Stations to say that they're like, I don't know, a few minutes younger or older, or I forget which way it goes, right? Than people here on Earth. And I thought, with such short life cycles of like bacteria, then does that increase the impacts of those small effects such that they would actually be measurable, and you could compare two separate populations, like one on Earth and one on the space station, and compare them and see that they are measurably different in age in terms of their biological age. So I thought that was something that would be really cool to investigate, and maybe there's someone working on it already.
Yeah, that's awesome.
Yeah. It sounds like this in and of itself is a cool thing to discover, to investigate. May not be related to simulations, but that's okay. I mean, that's a cool field. By the way, the closer you go, the stronger the gravity, the slower you age. So that's the principle.
Yeah, it's awesome.
Also the
I always
speed,
wonder
so
what would happen if you like were on the event horizon of a black hole. Would you just freeze in eternity?
yeah, so that's when physics breaks down. We don't really know what happens.
Yeah.
That's why it's black in pictures.
I love the way this conversation is gone. We've ended on a very cool topic here.
Yeah, we could almost have a whole new session about this, like biophysics and well, I don't even know. Would you call that biophysics, or is it something completely new? I don't know.
We can come up with a catchy new word for it, create our own
Bioastrophysics or something.
There you go.
Yeah.
Bioastrology. Oh, actually, astrology's the hippie shit, right? Damn, I've been recorded saying that. Cool. I know we've only got a couple minutes left, but if I could ask one more question, what and maybe this is something to end on. What's something you're most excited about in synthetic biology, in the grand scheme and landscape of things?
Yeah, I mean, I'm excited about some of the experiments that are planned at the ISS. Some of the things that are going to be happening. They just released this morning a company that's going to be working on therapeutics in zero gravity. There's a lot of cool microbial experiments that are planned. I'm interested to see kind of what the discoveries are from that. What insights are to be gained. Thinking about how the physics dynamics change. How a ribosome works in zero gravity is very different. Can we get novel proteins? Can we find new physiological phenomena under different constraints and then apply those to different systems? I'm really excited about that stuff that's going to be happening. There's also another private company that's going to be making a new arm of the ISS and then maybe replacing it called Axiom. Maybe you guys are more familiar even than I am, but they've got some cool, they're working with a bunch of cool companies sending stuff up there. So that's one of the things that I'm very excited about is seeing what happens with some of that. Maybe I can send some experiments up. I've got some ideas.
I'm sure we'd all love to do that as well. Maybe that's a whole there's, I don't know if you've heard of Space BioDAO, actually. That might be up your alley.
Space BioDAO.
Yeah.
Oh my goodness.
Yeah.
See, they've got a whole DAO dedicated to it. Yeah, okay. There's a lot of excited people.
Yeah. Yeah, we're trying to get I think it's Sarah Rouse is the founder, and I think she's coming to Montenegro next month. So we'll be trying to form a stronger bond there.
That's awesome. Cool.
Cool. Well, I think that makes sense to end there. Thomas, do you want to close?
Yeah, well, it looks like a lot of people have already left, but to those who are watching this later and made it through the questions about relativity in biology, just want to say thank you to Dr. Vaught for coming and talking to us. Really cool science, and I'm definitely going to keep up with that, and I think all of us should. But for now, let's just say thank you for coming to Science Spotlight.
Thank you, guys. Thank you for having me here.
It was our pleasure.
Bye, everyone.
Bye, all.